Hello, everybody. My name is Christian Jandl. I'm an application scientist at ELDICO Scientific, and I will share with you the presentation that I gave at this year's European Crystallographic meeting in Poznan. So we are going to talk about the use of electron diffraction to analyze phase mixtures, especially in the area of mechanochemistry. So mechanochemistry, for those who haven't heard of it, um, has the basic idea of using mechanical stimuli, which can be milling or grinding, to prompt chemical reactions. It is a very simple and fast procedure, and it is also environmentally friendly because you're avoiding the use of any solvent. And if you use solvent, it's just in very tiny amounts. So this reduces the amount of waste produced. And you're also saving a lot of energy because it is not necessary to heat the reaction mixture. And this allows certain reactions that you couldn't have in solution, maybe because at the point where you cross the activation barrier, you already get thermal decomposition. It also gives access to certain polymorphs that you cannot obtain in other ways. But of course, from a crystallographic point of view, there's one huge challenge because the mechanical forces that you have in milling or grinding or whatever reduce the crystallite size, which brings with it a lot of challenges in the crystallographic analysis. So we always have to deal with nanocrystalline powders in such cases. So we are in the area of nanocrystallography, which we define here as crystallography with particles that are below 1 micrometer in at least one dimension. So, of course, the standard method for structure determination, single crystal XRD, requires a certain crystallite size, which is usually around a minimum dimension of 1 micron at synchrotrons. But if you go to in-house sources, then you typically require crystals that are at least 10 micrometers in size. So single crystal XRD is just not usable for nanocrystals. Then we have powder XRD. This is, of course, the standard method for bulk powder analysis. It works with nanocrystalline powders. It is available because there is an instrument in almost every institute. You can do phase matching and quantification with this. This is all very well established, but it gets very challenging if you have a mixture with an unknown compound, because then the structure determination of this compound is basically impossible. So you can't really apply this if you have a novel structure in your mixture. So this is where 3D electron diffraction comes into play, because it can work with nanocrystals and it can give you a full structure elucidation even of minor species. Another benefit, it can even do absolute structure determination, as we will see later. And the principal idea is that you can treat any crystallite in your powder as a single crystal because you can select it with your electron beam and then collect diffraction data just from this crystal. So this is a method of choice if you want to do structure determination in mixtures. Let's look at how the procedure works. So here we see a very simple sample preparation. We take a standard TEM grid. Then we can place it on a sample holder. Here we see a microscopy image. So this is a scanning transmission electron microscopy. So this is the mode of choice if you want to reduce the dose on your crystals as far as possible during imaging. Then we see a lot of crystals on this grid. We can zoom in to the individual meshes and then zoom in again to an individual crystal. And here we see an illustration of the beam position with a diameter of 750 nanometers. So it is easily possible just by pointing the beam at a crystal to select just an individual crystal for illumination, from which we then can collect diffraction data. If you have different species, you can later group them by the unit cells that you determine and then perform a structure determination for each of these species in itself. So it's a perfect tool if you want to identify minor species in a mixture, which can be byproducts or decomposition products, impurities, and maybe also minor polymorphs of the same compound. So Here we can see a video of automation because this is highly desirable if you want to measure a lot of crystals, and this is exactly what you have to do if you want to analyze a phase mixture and still get enough data even from the minor species. So here we can see the procedure start. Basically, all steps of the measurement can be partially or fully automated. So we see the software here selecting the meshes where to measure. Then we will see it select the crystals to measure. See, they all get a numbering here, and then they will be measured sequentially. The software also does a centering of the particle. So first we will get it into the middle of the image where the beam is located. And then we will do a centering. So we rotate a little bit. We will see the crystal moves out of the beam because it was not in the eccentric height, which is then corrected by the software here. So now we have the crystal in the eccentric height, and we can perform a continuous rotation data collection, which we see start here. We see very nice diffraction. The particle is maybe not fully single crystalline, but it is still a very good data set with high resolution. We're using a bit smaller measurements, just calling 30 degrees here to show this video in a reasonable amount of time. And we already see we're moving to the next particle. So here the software moves to the edge of the particle because it is a bit larger and might be a little bit too thick to measure in the center of the particle. Again, it performs centering. So now the particle is in the eccentric height. And now the software will move to the starting angle and again perform a continuous rotation data collection from minus 30 degrees to 0. And then after that, one could do all the steps of the data evaluation, determining the unit cell, clustering the data sets by unit cells, integrating the data, selective merging according to the unit cells, and finally a structure solution. Now to some real examples. So here we have a supramolecular organic framework based on this tetrakis pyridyl phenylmethane. So the empty framework is already known, and what our collaboration partners did is fill it with a solvent, in this case benzyl alcohol, by liquid assisted grinding. You see, it's a very fast reaction, just performed within 20 minutes. And then if we do the analysis of the product, we can first see the unit cell changed as compared to the empty framework. So we can clearly differentiate the unreacted framework from the reacted framework. And in the reacted framework, we can see the voids now filled with a solvent. So basically, this framework has a breathing mode. It expands upon exposure to a solvent. So this was a rather easy example because here we were interested in the main species. Let's now get to examples where we are interested in the minor species. So here we have a synthesis of a salt. Again, via liquid assisted grinding, we're interested in this tyrrhenium fumarate hydrate. The structure of it we can see here. So this is the main species. But if we perform a mapping of the crystals in the reaction product with ED, we can also find impurities. One is expected, so this is simply unreacted fumaric acid, but we can also find some other crystals, which are also clearly distinguishable by their needle-like morphology. And we do find the chloride salt of one of the starting materials. So basically this tells us via one of the starting materials, there has been a chloride impurity introduced. And we just had one individual crystal here, and from this crystal we could perform a full structure determination of this impurity. The next example, again, is a mechanochemical synthesis. So we are synthesizing kininium aspyrinate. So it's an API salt, and by neat grinding, and we see we get an amorphous product, which in this case is desired because amorphous compounds have advantages for bioavailability. But it was observed that within 2 years, this amorphous material converts to the crystalline form. It has also been observed that this can be very much accelerated by exposure to liquid vapors. And if you do liquid-assisted grinding instead of neat grinding, you can just get the crystalline material from the start. But as I said, in this case, crystallinity is not desired, and some seed crystals can also accelerate a conversion of an amorphous material into a crystalline one. So we would like to exclude the presence of such seed crystals, and this brings us to the question: how amorphous is a sample that we can see as amorphous in powder X-ray diffraction? So we prepared a fresh sample. We can see it's X-ray amorphous again. We see a few discrete peaks, which can just be assigned to pure aspirin, so one of the starting materials. So then we performed crystal mapping with electron diffraction, and we see an image here. As we expected, most of the particles, they do not show discrete Bragg peaks, so this is indeed amorphous material. But we did also find some particles that show pretty good diffraction quality. So from this, we could easily determine a unit cell and match it with a known one for kininium aspirinate. And in this case, actually, a determination of the unit cell is quite important because we know that there is crystalline aspirin present too. So by unit cell determination, we can clearly assign this particle to the crystalline form of our salt. And this proves that we have actually seed crystals in a material that seem to be amorphous for X-ray diffraction. So we wanted to investigate amorphous samples with ED a little bit more and looked at amorphous samples prepared by different methods. In this case, the example compound is carvedilol, which is a beta blocker. The first method used was melt quenching. Again, we performed the crystal mapping. We can see just one example crystal here. And in this case, we did indeed find that all particles are amorphous. We didn't see discrete Bragg peaks from any particle. The material can also be amorphized via ball milling. And again, if we do the crystal mapping, we will see that most particles are again amorphous as desired. However, we did find some particles that show clearly crystalline pattern with discrete Bragg peaks. It's even nicely single crystalline, so the material is good enough to do a structure determination even. And in total, we looked at 91 particles in this case, and 26 of them showed crystallinity, 2 of them even such high crystallinity that can be used for a structure determination. So what we can learn from this experiment is that only one of those 2 methods is really suited to get a fully amorphous material. And if we want to use the other method, ball milling, we would at least have to increase ball milling time to make sure we get a full amorphization. Let's move to another example. So in this case, it's about a polymorphism, and we are looking at ritonavir, maybe the most notorious case of a late appearing polymorph. So this is an HIV drug that was marketed in 1996. But around 1 year later, suddenly a second polymorph appeared, which was more stable. And because of this, unfortunately, also less soluble, which made it less bioavailable. So it basically was useless for medication. Unfortunately, the seed crystals of this second polymorph already contaminated all the production lines. So it basically was impossible to reproduce polymorph 1 after this point. And eventually this led to the drug being withdrawn from the market, and it had to be reformulated, which of course cost the company a lot of money and reputation, and also lost all the patients their treatment for a certain time. And this is why pharma companies nowadays are spending a lot of effort on polymorph screening to avoid such polymorph catastrophes. Nowadays, even 2 more polymorphs of ritonavir are known. I'm excluding the solvates here. One of them, form 3, is fully characterized, and there's another form 4, which is not fully characterized, but it has already been patented. And together with our partners at Merck, we became interested in this form 4. It proved quite challenging to reproduce the preparation of it that was described in a patent. So unfortunately, it could not be obtained in pure form. It was always a mixture with form 1. So this makes it a perfect case for ED to perform a structure determination on a minor species in a mixture. And what our partners were also interested in was comparing this polymorph with crystal structure predictions that they performed on this case. And we'll have a look here. So we had to measure quite a lot of particles, 133. Of this 133 particles, we could only identify 17 as the desired form 4, and 13 of these had a suitable quality to be used in structure solution and refinement. We could indeed get the structure. If we compare our unit cell with the one predicted by CSP, we see a reasonable agreement. It's not perfect, so especially the beta angle has some deviations from the prediction. And what is also important to note here, if we look at the resolution, it was rather low, just as the completeness. So this was quite a challenging case for a structure solution. And indeed, ab initio methods failed in this case. But we could determine the structure first by simulated annealing. And we could also determine it by using the model from crystal structure predictions. Let's have a more detailed look at the crystal structure predictions. So here we can see the 26 best predictions. Indeed, form 2 is predicted as the most stable one, more stable than form 1. So this basically shows that with today's level of crystal structure predictions, the ritonavir polymorph catastrophe could have been predicted. But we also see the form 4 that we are interested in here. And actually we see that both form 1 and form 4, they appear twice because there is this disorder of an isopropyl group that basically leads to the prediction of two structures that are almost identical in energy for these two cases. Let's go to another example that utilizes one of the additional benefits of electron diffraction, because electron diffraction can also be used for absolute structure determination via dynamical refinement. So the field that we want to apply it to here is conglomerates. So as a quick explanation, if we just have a racemic mixture of any compound and we crystallize it, in most cases, we will get such a racemic crystal of both the enantiomers in the same crystal. However, it is also possible that we get separated enantiopure crystals as illustrated here. So this is what people call a conglomerate. And such conglomerates are useful because they can be used for chiral purification in the solid state. However, they are also quite rare. So we see just only in about 5% of cases we get the formation of such a conglomerate, which makes screening for conglomerates quite a tedious task. And it usually is based on a multi-method approach that uses second harmonic generation, IR spectroscopy, DSC, powder XRD, and single crystal XRD. So it is a very lengthy process. So we wanted to prove that electron diffraction can directly identify a sample as a conglomerate. And the idea is shown here. So basically, we use the power of electron diffraction to measure individual crystals in a mixture, and then we perform an absolute structure determination. So if we then find both enantiomers present, as is illustrated here, this basically proves the formation of a conglomerate in this case. And we can have a look at an example here. So we use this chiral sulfoxide, measured 12 crystals, and then the idea is to perform a dynamic refinement for both enantiomorphs and the correct enantiomorph will give a better fit with the data, as we can see here in the R factors. So for example, here in the first line, we have roughly 2 percentage points better in R1 for the correct enantiomorph. Now, if we go from crystal to crystal, we actually see sometimes we get the S form, sometimes we get the R form. And this is not a consequence of bad data quality that we couldn't really decide which is the correct one, because if we look at the statistical validation of these absolute structure determinations via the Z-score, they are all very high. So 3 sigma are usually seen as a threshold to give a reliable result, and we see through the bench we are far above this value. So we can see a very high figure of merit for each individual absolute structure determination. And these absolute structure determinations produce different enantiomorphs, basically proving that we have both forms present in the sample, and therefore we have identified it as a conglomerate. Okay, with this, let me summarize this talk. So we saw that electron diffraction is a very powerful tool for the analysis of phase mixtures in the field of mechanochemistry, but also far beyond it. It can work with nanocrystalline powders, very small sample amounts, and the real power is in the analysis of individual crystals in this mixture. The measurement times are very low. It's typically 1 to 2 minutes per individual crystals, and it can even be automated for high throughput. We do not only get a full structure determination, but we can even determine the absolute structure if we use dynamical refinement. Here you can see our instrument that we use for these studies. This is the dedicated electron diffractometer designed by ELDICO Scientific. If you are interested in the details, feel free to get in touch with us. And so finally, I want to say thanks to all our collaborators who made this work possible, and I want to thank you for your attention.